Hello everyone, in this video I'm going to feature conversion factors that convert between units of measurements in the traditional measurement systems. That is, we're going to be talking about conversion factors that work between gallons and cubic inches and pounds and those type of measurements, both in the Imperial and the US customary systems. Yes, those are different. So, there's not going to be any mention of metric, only as reference in passing. Okay, so cubic inches, cubic feet, gallons and pounds are going to be featured in this video, and the conversion factors will only work for these units. The point of this video is that these conversion factors that are going to be on the left hand side of the board in red color, so 10 numbers, those can be listed here real simple. That takes less than a minute, but the explanations are going to come up on the right hand side. What kind of explanations? Have you ever wondered what those numbers mean and where they come from? Weird conversion factors often have multiple decimal places, and they are not coming from people who sit in white lab coats and scheme about making life miserable with difficult numbers. No. All of these conversion factors have a rational or reasonable explanation. Sometimes it involves history, sometimes it involves a couple of mathematical relations, fairly straightforward, just divide two numbers to get a third one type thing. Okay, so it's not going to be overwhelmingly complicated. But sometimes history and sciences are involved in the explanation. So, on the layout of this video, the conversion factors will be here, left side, and we're going to do two at a time, so in pairs, so 5 sets of 2, and the explanations are going to be there. I'm going to make them big print so it's easy to read, but on the last page I have already pre-made the slides, so it's going to be smaller font, compressed, all that it fits the board as is on one page, all 10 conversion factors with their math calculations or explanations there. The reason why this video is created is for twofold. It might make it easier for you to just comprehend these conversion factors, and comprehension might turn into motivation. Okay, because if you're sitting there being angry at these numbers that they don't make any sense to anybody, that's how they look like, that's a good start. But there is a reasonable, logical explanation behind these numbers, so the fact that these are explained, it might help learning and it might aid memorizing. Whether making the conversion factors sensible actually helps, or how much it helps with memorizing, it's up to you. It depends on everybody's different. So whether the math stories that unfold will actually help you remember the conversion factors, that again, I don't know. However, the conversion factors that are going to be featured here are used in a number of trades or occupations, and these occupations typically are construction occupations as well as transportation occupations. So if you're involved in constructing vessels that contain fluids such as pipe fitting, sprinkler fitting, even gas fitters have to go through some of these, plumbing, boiler making, metal fabricating. So these types of trades that contain or that construct containers for fluid capacity, and anything in transportation. If these fluids are transported through pipelines, any other number of occupations in the pipeline industry, whether it's being transported eventually not only through pipelines but through ships, container ships, tanker trucks on road, even by air, and especially also by rail in railway cars. All of these, or a number of occupations in transportation, might involve doing math with these conversion factors. Again, I'm not showing you how to use the conversion factors. I'm explaining where they come from just to make math sensible. Alright, that's a long intro. Let's get started with the first two. Imperial gallons and US gallons and cubic inches. Fairly straightforward. US gallon has fewer cubic inches, Imperial gallon has more cubic inches. Okay, good thing. There are 2 gallons in commercial use. Just in case it wasn't explicitly stated previously, this automotive fluid here is sold in a US gallon amount, and this automotive fluid yonder is sold in an Imperial gallon amount. The container doesn't say US gallon on it, but it does say one other thing on it. It says 3.78 liters. Like I said, it's not going to be about metric, so that's just for a reference, 3.78. And the other one is also doesn't say this is Imperial gallons, and it says 4.4. It could say 4.5. Either which way, don't worry about it. This is just labeling. It's obvious that this is Imperial gallon, and this is obvious it's US gallon. The US gallon is skinnier, 3.7, 4.4, 4.5, whatever. You get the idea. 2 different gallons in commercial use. The cubic inches are a unit of volume. So we're going from fluid capacity to volume, and these cubic inches are a unit of measure of space, empty space, even though this cubic inch here is made of aluminum or aluminium depending on the market. It's 1 cubic inch because it's 1 inch wide, 1 inch tall, and 1 inch deep. It's 1 cubic inch of space. It doesn't matter what it's made of. It could be made out of ice, whatever, frozen beer, whatever. What's important is that 231 of these little guys make one of these US gallon, and 277 of these make an Imperial gallon. So now, why these numbers? Where do these come from? Well, we start with 231. It is by definition 231. They just picked a whole number, not entirely randomly. This is coming from 1706. I kid you not. This before it was called US gallon, it was just known as gallon, the only one, the only kind of gallon, and it was 231 cubic inches. It has a long history, and at the last time it was defined this way, like I said, was 1706. I'm not making history up, I'm just telling you as it is. It was decided, they picked a whole number at least without a decimal digit, so that's good. The Imperial gallon has it's an infinite decimal number and has more digits. This 277 comes from a division fact. If you divide 10 by that other number, you're going to get 277 plus change, all of the decimal digits. So what are these 2 numbers? The black one, 10, is a number that was purposefully picked. 1 Imperial gallon was defined in 1824 as the amount of space, any amount of space, 10 pounds of water, pure water, and more about it later, 10 pounds of water wants to take up. So whatever shape and whatever space 10 pounds of water takes up, there's also other conditions relating to temperature and pressure. That's going to be 1 Imperial gallon. So they picked a whole number, 10, and the rest of it is an infinite decimal number. This purple number here is the density of water at the same temperature and pressure as the 10 pounds is measured. And this density of water is a natural phenomenon or a natural fact. Nobody chose this number, it just happens to be so. Sorry about the fact that nature doesn't coincide with whole numbers or convenient whole numbers. That's the density of water per cubic inch. So if this is filled with pure distilled water, no mineral deposits, because the mineral particles make it heavier, so this is pure water at a set pressure and temperature, that's the density of water per cubic inch. So that's the first 2. The next 2 are going to be easy and fast. Imperial gallons converted to US gallons and back and forth. 1.8 and 1.2 and 0.8 are inverses of each other, and the calculation is fairly straightforward. Using the previous numbers, you divide the 277 plus change by 231, you get 1.2, and you do the long division. You do the division the other way around. I hope you're not dyslexic. Then you're gonna get 0.8 plus change, because this number is an infinite decimal, the results will be both infinite decimal numbers. They are typically rounded to 1.2. You'll try it on a calculator, do try it. You're going to get 1.20009 and the rest of the digits. Same with this 0.8, so they are often rounded. Only two numbers in this whole conversion factor lineup are whole numbers, the 10 and the 231. That's it. Everything else is infinite decimal numbers. Sorry about that. The next two numbers are these two, Imperial gallons and US gallons, and we are going to be discussing these 10 pounds situation that came up earlier. So I said it's pure water, but there is more to it. The conditions spelled out, I said temperature and pressure is involved, is this. So pure water at 62 degrees Fahrenheit, not 1/10 higher or lower, and at 30 inches of mercury of barometric pressure. That's how originally the gallon was defined in 1824. Since then it was refined a little bit, the definition, the numbers, one number is slightly different. More about it later. Very briefly, so this 10 pounds was picked, and those 62 and the 30 goes with it. You kind of have to remember the conditions with the figure 10, and the reason for it is that if you have a scale, and I just have a convenient scale like this one here is digital, you can weigh your fish with it. Any scale, but this fits the camera's view here. Any scale is affected by temperature and pressure. Let's start with air pressure. Air pressure is going to be pushing down on the container. It does matter at what altitude you take a measurement, because air pressure drops as you go higher up in the mountains, so how much air is pushing down on the surface of the container in which this 10 pounds is. I know I grabbed the US gallons, so let's grab the Imperial gallon there. This is actually 10 pounds plus the container's weight, so that air pressure that's pushing down on the container is important. Why temperature is important is because with temperature the fluid inside expands sideways. The molecules bounce more and they take up more space. It's going to be the same 10 pounds, but it's going to take up more space. So if 277 plus 42 whatever decimal digits filled it to the brim, if you heat it up at 62 degrees Fahrenheit, that's 16 and 2/3 degrees Celsius. If it's filled to the brim, and if you heat it up from 16.6 Celsius, 62 degrees Fahrenheit, to, I don't know, 100 degrees Fahrenheit, it's going to overspill, it's going to run down here because it expands and it's going to just run over. So that's why 10 pounds of water at higher temperature will take up more space. So that's why it's important that it's 277 inches plus change only at this temperature and at that air pressure. This air pressure is what their best guess was in 1824 for mean sea level or average sea level air pressure all over the earth, everything averaged out. Also the gravitational pull of the earth is also taken as averaged out. It is different at the equator, it's different at the North Pole, at the South Pole, so it's taken at 45-degree latitude, something like that. So it's halfway between the equator and Santa's workshop. There at normal gravitational pull, not on the moon or anywhere else. So that's the story with this 10 pounds. You kind of need to work with the fact that temperature and pressure change the weight of water. The 8.3 pounds, I don't have a story for it. 231 is the cubic inches that we discussed before, and that purple number is the density of water again. That was featured in the first calculation up there. You can just barely see it there. So it's the same number, same digits, infinite decimal number, so 8.3 plus the rest of the decimal places, typically rounded to just 8.3, because for most calculations it's accurate enough. The next two are going to be more of a stories, cubic feet. The first one is easy. This one is involving some more stories. A cubic foot is 1,728 cubic inches. It's a math story. A cubic foot is a shape. There we have it. It's a plywood box, OSB, whatever. It's a measure of space. Again, it doesn't matter what it's made of. What's important is that it be 1 foot tall, 1 foot wide, and 1 foot deep in this 3 directions. So this is 1 cubic foot of space. If you want to fill it with cubic inches, you need, of course, 1,728. Now 12 inches do make a foot, but 12 of these cubic inches don't make it too far. 12 of them will only make one line here up top. So 12 of these is not going to fill the whole cube. You're going to need 12 rows of 12 just to fill one side of this. So 12 times 12, it's going to be 144 of these cubic inches on just one side. And then you need 12 deep as well. So 12 times 12 times 12, 1,728 is what you see here. Let me just click on the math story there. That's what you see. 12 cubed is that number. The other number, 62.42, is pounds of pure water. Again, we have another poundage or weight situation that involves, again, temperature and pressure. This time, though, it's different. Instead of 62 degrees Fahrenheit, it's 39 degrees Fahrenheit, which is 39.2, whatever, which is exactly 4 degrees Celsius. It's actually not exactly, it's 3.98 or something like that Celsius. So where water is densest at that temperature and at mean sea level or average sea level in normal gravitational 45 degree Earth latitude, it's gonna be, if this cubic foot is filled with water, it's gonna weigh 62.42 pounds. Now your textbook might say 62.43. It can be rounded. It's better rounded to 62.43. I indicated it that way in the corner with a red digit. But if it's 62.42 in your textbook, close enough. Just go with it. So this is a figure again where water is densest at that temperature. And what happened to the 30 inches of mercury? It went down to 29.92 because it's been revised. Since 1824 we have better measurements for measuring the mean sea level air pressure at all of the heights of the oceans, from high tide to low tide, and all of the oceans averaged out. We have better surveying data, and it's slightly different. Instead of 30 inches of mercury, it's that number, which is also equivalent to about 15 psi. You might have it in your textbook as absolute gauge pressure, or that many kilopascals. It could be millibars, 1013.25 millibars, whatever. So the same pressure at mean sea level. You get this number 62.42 if you divide those two purple numbers by each other. Where do those purple numbers come from? It's a mouthful, but it's straightforward. This one is 1 ton, metric ton, 1,000 kilograms. And 1,000 kilograms divided by, this is 1 pound, converted to kilograms, and it does not have any more digits. So this is fixed number of digits that you see here, all 8 of them. When you divide these two numbers, you're gonna get what's 1 metric ton in pounds, and you divide this by 35. What's 35? 35 of these cubic feet fit into a cubic meter, plus change, 0.3. So a cubic meter, just like this cubic foot, is a cube that's 1 meter by 1 meter by 1 meter. So it's a biggie. It doesn't fit in the camera's view here. And 35 of these cubic feet fit into a cubic meter. The length of an inch is 25.4 millimeter, so 12 inches make a foot, so that's 1 foot cubed. and that figure 1000 relates to the fact that that's millimeters, and it's going to be actually cubic meters, so that's why that's 1000 there. You're going to get 35 out of it. You do the division, you will end up with 62.43 for the weight of 1 cubic foot of water. Last two numbers are fairly easy. 1 cubic foot converted to imperial gallons and US gallons. This means that in terms of imperial gallons, which is the bigger one, 4.4 liters on the label, 4.5 liters actually. 6.23 of those ones fill and fit into one of these cubic feet. And with the US gallon, because it's smaller than the imperial gallon, more of these will fit into a cubic foot. You need 7.48 of them. The calculation for them is fairly straightforward. There. These numbers come from the fact that 1,728 of these cubic inches make a cubic foot, and you do this division with infinite decimal numbers, you will get two decimal numbers. Both of them are infinite for math reasons. So that's the 10 conversion factors. This is the last page here where everything fits on there, where everything fits in the camera's view. So that's all of them: the 277.42, 231, 1.2, 0.8, the 10, the 8.3, the 1728, 6242, 6.28, and 7.48. You know what? There's a third number that's also a whole number. 1728 is also a whole number. Alright, so you have 3 whole numbers and the rest of them are all infinite decimal digits. So that's what the conversion factors are. That's where they come from. It may help your memory, or it may help you memorize these ones if you recall some of these stories. Some of them are obviously simpler, like 12 times 12 times 12. Some others need memorizing the density of water. Yeah, probably don't bother. Just work with the 8.3. It's easier to remember that. So, you know, mix and match. Whatever makes the most sense to you personally is what's going to be most useful to you. So thank you very much for watching. That's my story with the conversion factors. And how you use these conversion factors, completely different video. I'm going to include a link in this video's description box below.